So let's talk about average treatment effects and how we might solve it. So firstly, let's talk about the types of average effects that we are interested in observing. So firstly, there's something called the average treatment effect on the treated. So it's called an ATT. Yeah, so average treatment effect on the treated. So what we do is, it's written as the expectation of the difference between the potential outcomes of the treatment subgroup. What that means is, we go back to our business salesman case and we only take this treatment subgroup and then we subtract their potential outcomes. Again, this is not observed because obviously for the same person we don't observe both their potential outcomes, but this is the definition of an average treatment on the treated. So naturally, what would be the average treatment on the untreated? I'd like you to pause the video and try to write this equation down because it's helpful to remember these notations. But average treatment effect on the untreated is simply the expectation of the difference of their potential outcomes of the subgroup that is not treated. Right? This makes sense? Now, we also have an average treatment effect. The average treatment effect simply expands the average treatment on the treated to the entire population. So it's kind of like combining ATT and ATU, and that's just saying it's the difference of the potential outcome of the whole group. So now we don't just separate the group by treatment and control, we take the whole group and we are interested in the difference between their potential outcomes, right? In most research, ATE is our primary factor of interest. Now, how might we understand or calculate ATT or ATE given what we know? So let's write down what we know. What can we observe? So take a look at your notes and try to think about what is observable in this world. Obviously, what is observable is the observed outcome, which is this term over here. More specifically, the observed outcome of the treatment group and the observed outcome of the untreated group, right? So essentially, I can take the average of the observed outcome on the treated group, and I can subtract it with the observed outcome of the there was a glitch, I'm sorry, but I was saying that we can take the observed outcome of the treated group and subtract it with the observed outcome of the untreated group. This is possible, this is in our hands, right? Now, how may we do some modifications to this to get what we want, which is ATT or ATE? We would prefer to have either of them, right? So remember and recall that I told the observed outcome can be written as a function of the potential outcome, right? So let's do just that. Let's take this observed outcome and try to write it as a function of the potential outcome. Oops, wrong color. Yeah. So if I write that here, let me write the first term down. Yi will expand it as yi of 1 times di plus 1 minus di times yi of 0. Oh, shit. Given that di is equal to 1. Remember, I'm still just writing the first term. There is a second term that's coming. And I can subtract to it the second term. But before that, let me just shorten this first term. So firstly, you can see clearly that it's di is equal to 1. So let's just substitute that. So this would be 1 and this would be 1. Oh, this would be 1, which means obviously this term will become 0, which means that this term will no longer be there, right? And of course I can remove this one as well. So I can reduce this and write it as potential outcome of the treated. Okay. Similarly, let me do it for the second term. If you didn't understand it from the first term, maybe the second term, when I do it for the second term, it will make sense. So again, I write the same formula, yi, and as a function of the potential outcome of 1 plus 1 minus di, 1 minus di of y0 given that di is equal to 0. Again, so here we have a condition that di is equal to 0, which means that this term we can replace as 0, which means this term can be replaced as 0, which means that this whole term will go away because it's being multiplied by 0, and what remains is just this term. So I'll bring that over here. Okay, so this is our observed outcomes written as a potential outcome, written in the form of potential outcome. Now also look closely here. This, what is this really saying? It's saying this is the potential outcome had you been treated in the subpopulation of the treatment group. Okay, and this is the potential outcome had you not been treated in the subpopulation of the untreated group. Okay, now what sort of manipulation may we do here? Here's a little neat trick. We are going to add and subtract it by an interesting term. So firstly I am going to write the first term as is. Now I am going to add to it, I'll subtract first. So I'll subtract to it the expectation of the potential outcome of not being treated in the treatment group, and I'll add to it the same term. I'm just adding and subtracting, just algebra here. Okay, and now I'll write my second term again. Now here something interesting has already happened. If you notice some pattern here, like pause the video and check if you can notice the pattern that I'm suggesting. But what has already happened is this first term, this is the ATT. We described it just above. You can see this. This and this are exactly the same. This can be rewritten like this because of linearity of expectations, but they are exactly the same. So this first term is the ATT, and the second term is called the selection bias. Okay, so what we need is the ATT, and what we can observe is this. So the way I'll write it is, or I'll use white again. The way I'll write this is the expectation of the differences between our observed variables okay, can be written as a sum of ATT and selection bias. Okay, so in a sense, ATT can be written as observable difference. I'm going to name this thing observable difference minus selection bias. Now, how will we find ATT? We have to justify and make selection bias to be equal to 0. If selection bias is equal to 0, if selection bias goes to 0, ATT becomes observable. Now, the neat thing about a randomized control trial and other techniques is that it is trying to make selection bias to be equal to 0. Now, let's go into a bit of a conceptual review here on what selection bias is. Try to read this equation out loud. It essentially is talking about the potential outcome of not being treated in the treatment group minus the potential outcome of being treated in the untreated group. Now, when will the selection bias be equal to 0? When this whole term is equal to 0, which also means when the potential outcome in the treatment group, the potential outcome of not being treated in the treatment group is equal to the potential outcome of not being treated in the untreated group. Okay, what does it actually mean? Your potential outcome in counterfactual would have remained the same whether you are in treatment or not. Okay, no matter if you're in treatment or not, your potential outcome had you not been treated would have been the same. It is kind of like saying if you have a group of people, let's take our businessmen itself, no matter the assignment, so no matter if I assigned my blue businessman in the treatment group or I assigned the blue businessman in the control group, their sales would have remained the same no matter the treatment assignment. They would have always had the same amount of sales in a world where they never got the treatment. Okay, so it's kind of like saying that the group that is in the treatment is not inherently different from the group that is in control. If the ATT is positive, right, if we could estimate it and it is positive, then what does that mean? It means three things. It could mean three things, and this is a little glitching. It could mean three things. One could be that the DI, which is treatment, has an effect on the outcome. So it could be that the treatment has a causal effect on the outcome, or maybe the outcome has a causal effect on the treatment. This is called reverse causality. Or it could also be that there is a third confounder that is affecting both the treatment and the control.